let's get going a little bit. We're recording, right? Awesome. First, I messed up a little bit last week. I said the next assignment was going to be on the properties of the CA code. But I'm moving a little bit faster here. So then this one we're going to start with today is the acquisition challenge. But you're going to get 2 weeks to complete that one. I will post it later today. I have the data set, but I just got to figure out just how difficult I made it before I decide on grading levels and stuff like that. I post it later today, together with the next set of groups. There also was a question about the projects I got from one of the students before the lecture started. We got until spring break, we will do lectures and assignment, and then we'll have the midterm, and with the midterm I want you to submit the project proposal, which is what we're going to be working on the 5 weeks after, or however many weeks it is, after the spring break, until the end of class. Any other questions? All right, let's get going. So today we're going to start talking about the acquisition. We touched on it a little bit yesterday, or last week, when we looked at the properties of the CA codes, the gold codes that we use for in GPS CA codes, how they worked, and today we're going to see what happens in a real receiver. So if we look at the generic GNSS block diagram here, I want to get this going, of course, because I like it. We have an antenna, we record very, very weak signals, and whatever noise, thermal noise is present at the antenna, and whatever else is transmitted in that band, that signal is input to the front end, where we do some signal conditioning, amplification, filtering, downmixing, and sampling. After that, it's passed into baseband signal processing. How many knows what baseband means? Hands up. All right, I'll go through it quickly today. It's not too difficult. And we also have a microprocessor that talks to the baseband processing, kind of controls the entire scenario, what signals to look for in acquisition, what signals to track back and forth. And then we have some user kind of actual measurements we make have to end up somewhere, otherwise we're wasting power. All right, and we talked about this earlier in the earlier classes. I've showed you the layout of the front end. This is just a more detailed version of the first block: antenna, filters, amplifiers, a mixer, ADC. All right, you remember weren't running on the same clock. And we also looked at the time domain plot of the data. Just looks just like noise. There's no apparent signal in here. Signals are below the noise floor, as we call it. Look at the spectrum of this particular data set. We have the kind of filter shape right here. And in the middle, we have the aggregate of all the signals that are transmitted. So each of them are below the noise floor, but together they kind of pop up above it. Does it make sense? Everybody's happy so far. See how this goes. Histogram looks just like noise. So, do we know if it exists? Now we're where we want to be. We have to do the acquisition first. We have to figure out, are there any signals in this data set? Where is he? There are 2 things we're looking for. The code phase, meaning what sample number into the file do the signal start at? Or this repeating code, where does the repeating code start? And the second one is the frequency of the signal. Because if you look at it, we have satellites orbiting the Earth. They move relative to us, so we have a Doppler on the signal. We also have a pseudo-Doppler based on the clock error of our front end. But it all adds together to be one carrier frequency that we need to figure out. And what we looked at last week, we just looked at We took 1023 ships long code, looked at the outer correlation. How does it correlate with each other? We saw there was a strong peak, right? We saw that they didn't correlate well with each other, meaning that it was only noise if we correlated the signal from PRN1, satellite 1, with PRN2, right? That goes for all the other combinations, but I can't be bothered to show you all. So that was a good example of something being at baseband. So when we talk about the signal processing, people talked about things being at baseband. The thing is that the carrier frequency or the carrier on the signal should have been removed. Similar to how the mixing is done in the front end. But that only gets it close, right? So we have a signal at 1575.42 plus a Doppler. And then we mix it in the front end. We multiply it with a sinusoid. We move it down to another frequency, right? But that only gets us close. We still have this Doppler and pseudo-Doppler to deal with. And that we do digital. So then we do another mixing process. But we multiply it with another carrier frequency, and then one of those sets that we test is going to bring the signal down to baseband with no carrier in it, or at least a very small frequency compared to the integration time. Does this make sense? I don't expect you to grasp everything, since this is the first time you hear about it. But it will all be clear. So, and if we go back up a little bit, acquisition, we need to search for each PRN code, we need to find the code phase and the carrier frequency. And there's a kind of rule of thumb here. We need to be within half a ship for the code phase and within plus minus 500 hertz if we integrate over 1 millisecond. And that is the length of the CA code, so that is where we start, and that is how the book code works. It's only 1 millisecond integration. Next step after that, we have the two loops that are intertwined, basically. The code tracking loop and the carrier tracking loop. We'll get to that later, and finally position solution, but we're not there yet. So still, I like to repeat stuff, basically. Repetition is the mother of all knowledge. From last week, we have a CA code, we have another. So this here is our local replica. And this is the data that we have recorded. Now here, of course, it's sort of noise-free to make it clearer. But this is what we do. We try to find them to line up, and here they lined up. So if we, before that, we would have been off a little bit, and then whoops, we find a peak. All right? So it's a little bit of a curse that the peak is so narrow. This is why we have to try every half a ship. So if we have a wider peak, then we would be able to find it faster, right? But a wider peak implies a shorter code, which is not desirable for other purposes. Then it's going to correlate worse with each other. All right? So it's a little bit of an engineering trade-off, like everything in life. Skip that one. This here is what we're going to start talking about. Digital baseband processing. What happens inside? And this is a block diagram of what that would look like as implemented in an FPGA. In Mathlab you can do it a little bit differently, but this is basically what it looks like. And I'm going to go through this in quite a bit of detail too, so you see what's going on here. So we get the samples from the front end. We all know that. I talked about we're having to mix it to baseband to remove the carrier on the signal, right? And that is done in those two mixers. We have a cosine and a sine. So it's basically the same sinusoid, but it's offset 90 degrees. I will explain why we need this later on. And then we have three others. So this is mixers that multiply each sample with the output of a sinusoid generator, basically. But it's just multiplication. We also multiply with the early, prompt, and late code. So we have a code generator, and this code NCO. NCO means numerically controlled oscillator. So we have something here that tells us we have a clock coming in, and then we generate another frequency based on that clock. And then we can control whatever that, how fast the code is generated. Does it make sense? Because that's what we want to control later on in tracking. But anyway, we get the code from here. We kind of shift it a little bit to get the early, prompt, late, 3 replicas. We multiply the outputs here, both the cosine and the sine. We also call them I and Q, in phase and quadrature. But it basically means the same thing. We multiply those with the code. We have an integrate and dump. So that basically means exactly what it is. It's you have the signal coming in, multiplied with a sinusoid, multiplied with the code, and then we just add up whatever number we have. So over time it's going to look noisy, and then hopefully it's going to grow a little bit at the end. This is what the sum was. So if we're in the right spot, then we should get a high value coming out of the integrate and dump correlators. If there's no signal there, it's only going to be noise. Does it make sense? So we have 6 of those. The in phase and the quadrature, early, prompt, and late. And this is then input to the microprocessor, and whatever the result is, the 2 things are steered here again. The code NCO and the carrier NCO. And this is how we move back and forth. But this is the FPGA kind of layout, where samples are streamed continuously. There is no memory needed really in this, other than in the integrate and dump correlators. All right? Does this make sense? So for acquisition, we control this basically. We check a couple of correlators, and we'll move forward a little bit, and we'll check another couple of ones. Eventually, hopefully, we'll find the signal. All right? But remember, there's a 3-parameter space: the PRN number, the code phase, and the carrier frequency. So it's not a very nice problem to solve. You don't want many dimensions in whatever problem you want to solve. Does it make sense? All right. And I think I want to do some Mathlab with you now. Let's see where we're at. Of course, I'll start with repetition again. Show you this last week. We add no noise whatsoever to the signal. We have the top part, can't point in Mathlab. The top part is our local generation. Oh, sorry, the noise one. Bottom one is the locally generated. And we find our peak. It's all nice. Makes sense. Go back. We had a lot of noise. Just looks like noise. We correlate. Come on. We still find it. Just more noisy. But eventually, if we keep on going, it's just too much noise and we can't find the signal. All right? The examples are actually a little bit later. All right.
Just a question. The
Yeah.
book says that there is a Simulink model for the GNSS receiver.
Ooh, does it really?
Yes.
All right.
But it wasn't, I think, supplied with the book itself or on the course notes. Do you know how?
No, I haven't actually seen it. I know the Danish guys who kind of put the book code together. They kind of like Simulink.
Because in the appendix, everything, or whenever they talk about something and they try to explain things, they are trying to explain it not based on the Mathlab thing, but the schematics like the ones that we have here are explained through the Simulink.
All right. Well, it's not on the DVD. I had someone ask for whatever was on the DVD, so I looked through the DVD and I didn't see any Simulink model. If you want to, I can email Kai Bore, the Danish professor, and see if I can get that one.
Okay,
If that is interesting. I don't think it's strictly needed, though. I've never seen it, actually, so supposedly you can understand stuff without it. But we have our samples coming in from the data set, and this is basically another way of looking at the acquisition. It's pretty much the same thing. We generate the code, multiply with the code. We have the INQ local oscillator, we integrate, we get the power out, we sum it, we have some decision logic. Does that make sense? What's different from the other block diagram I show you? It's kind of subtle.
The squared?
Oh, yeah, but that's not what I was asking for. You had to be psychic to know what I was asking for. They changed places, basically. The code and the carrier are multiplied. Here, it doesn't really matter what order you do stuff, right? Multiplication is commutative. So it doesn't really matter. And if we look at this one, I said we have a sharp peak. Looks extremely sharp in this one, but if we zoom in, we see that we actually have a triangle, right? Another question is, what is this distance? Anybody care to guess?
1 chip.
If you look at the x-axis, actually 2 ships. So it's 2 ships wide. Meaning that if we are perfect in our guesses, we're going to end up at the top, right? But since we don't know when it starts, we could end up somewhere else, which is why we need more correlators. So if we look back at the FPGA approach here, so we had everything happening in real time. And if we do 1 millisecond integration, we only have 1 channel. In order to find all possible signals in there, we have the 32 number of GPS satellites that could be visible. We have half a ship. I'm going to talk about that a little bit more in detail. So 1023, the length of the code multiplied by 2, times 10, which comes from the number of carrier frequency that we need to try. Right? So this comes down to the Doppler on the satellite and the accuracy of our local oscillator. If you look in the code, you have a parameter that says ACQ search band. That I think is set to 14. And that is actually plus minus 7 kilohertz. Does it make sense? Could it be plus minus 40? No, it's got to be plus minus 7, yes. And if we just multiply that together, we end up with a bit over almost 11 minutes to find all satellites, which is not very efficient. I mean, I have a GPS in my runner's watch. I can't really wait 11 minutes to start running. But if we add more channels, 12 channels, for example, we're down to 1 minute. My GPS in my runner's watch is still much, much better. And we're going to get to that, how to make this better. And we typically separate between a couple of different modes here. So I mentioned previously that part of the data that is transmitted from the GPS satellite contains information about where the satellite is at, right? We have the orbital parameters transmitted as part of the data message. And they have those accurate for that one particular satellite. And that is called the ephemeris. And they also transmit something called the almanac, which is a coarse estimate of the orbital parameters for all the satellites in the constellation. So once you have decoded the data from one satellite, then you can figure out roughly where all the other ones are. And this is called a warm or hot startup, meaning that we have some information. We know roughly where we are. We're basically going to assume that is where we're last turned on. We have some idea what time it is of day. We're not very accurate time-wise, but Might be off a couple of milliseconds, but it's no big deal. But we know roughly where we are, we know roughly what time it is, and we know the orbital parameters, rough, for the entire constellation. So we can remove at least half of this GPS satellite when we start looking for it. And we have some idea which signals should be the strongest, so we start with those and go on, all right? The cold startup is when we have no information whatsoever. Let's say we do a factory reset or GPS receiver, or we run the book code. That never matters about what happens last time. And then it's more, then this kind of assumption is more correct for the cold one. Does it make sense? So let's go to this here. Let me start, I prefer this one actually. So I know some students are a little bit, can I still do this? No, I can't. Can I? No. All right. Be more moving around here. So this is to basically illustrates what happens when we do the mixing. And I've typically had students struggle a little bit to find out what actually happens when we have this sine and cosine signals. Why do we need both of them to mix the signal down? Pardon?
Because they're orthogonal.
Well, yes, we'll show you here what happens. So let's assume that we have a signal that we're interested in, just m of t. Doesn't matter what it is. Just random signal that we're interested in. And we multiply this with just one, a sinusoid, right? Well, this is a signal that we have. We have a code, for example, m of t, and we have the carrier frequency sinusoid multiplied with that signal, whatever it is. Does it make sense? And we have some noise. And then we want to bring it down to baseband. Right? I've showed you the examples, what happens when you correlate. That is only valid at baseband. So we need to have a very low frequency of the carrier of that signal. So let's see what happens. We'll multiply it with another sinusoid. I put a wiggle on the omega just because it's an estimate. We don't know exactly what it is. It's a guess, basically. And this is what we end up with. If I had a whiteboard, I could have done it that way, but I would never have remembered whatever the rules are for the sinus and cosine multiplication. But we end up with this. We have omega t minus omega wiggle t. So if we guess correctly, everything is going to be fine, right? We also have the omega t plus omega wiggle t, which is going to be pretty off, right? The same way I talked about when we have the mixer in the front end. We start with a 1.6 gigahertz signal, multiply it with something close to that, we end up over 3 gigahertz. Here the offset is much smaller, we're still going to treat it as noise, right? So I put a wiggle on the noise just to sum these together. Keep going on. This is the same. And if we say that we are correct, we end up with this. Right? But we still got this phi left, right? So if we're off in the phase of our estimate, then we could end up with no signal energy whatsoever, right? If phi is pi over 2, we're screwed. Doesn't work, right? So now you see why multiplying with just one sinusoid wouldn't work in this case. And what's the difference between the front-end case that I talked about yesterday or last week?
What about the front-end case last week?
Well, the mixing in the front-end. There we only use one sinusoid, right? And now I showed you that it doesn't work with just one.
And the receiving end, it doesn't work with just one.
The difference is that in the front end, we didn't mix it down to baseband. We just mix it to another carrier frequency. Here we try to bring it down to 0. which makes all the difference in the world. Does it make sense? Because we never want this to happen in the front end. We have this, but we never assume this to be the same as this. So we never end up here. We're here. So we're still going to have a carrier frequency. That is, if we look at one of the data sets, the 16 megahertz one, we end up with an IF of like 4 megahertz. So even if we're off a little bit in our oscillator in the front end, we're still going to end up roughly 4 megahertz off. But if we want to bring it down to baseband, just one sinusoid just doesn't cut it.
Just a question, why?
Yep.
So it's usually this is called super heterodyne. So
Yes.
why do we choose the intermediate frequency? Why can't we just like immediately cut it off to the baseband frequency?
You can. I'm going to give you other data sets that work like that.
But what's the advantage of the super heterodyne? This additional step, because it costs us more hardware if we want to implement it.
Well, it's a couple of different things. It's maybe a little bit outside this class, but basically, super heterodyne is what is called when you mix it to another IF. So we have the 16 megahertz one, we mix it down to 4 megahertz, and then we do the rest in digital signal processing, right? We could do the same thing as what's happening on the next slide here, where we have two sinusoids that we mix it down with, an in-phase quadrature, sinus and cosine, and bring it directly down to 0. That works. The problem with that has to do with the physics of what happens inside the components, basically. So you're typically going to end up with DC biases, stuff like that. It doesn't have anything, in the ideal case, it doesn't matter what you do. They will work fine. But you do get some practical issues with that. But it's perfectly possible, and some people prefer it. But it's an engineering kind of trade-off, like everything else in life. All right? Anyway, I showed you it doesn't work with one sinusoid. Let's throw two of them in there, a sinus and a cosine. And I didn't go through all the steps, basically. But this is what we end up with, which is interesting. So, for starters, independent of whatever the initial phase of the recorded signals was, phi even if those are perfect, so we end up with 0 here. Regardless of what this is, the signal energy is going to end up somewhere. Either I or Q, or most likely a combination of both. Right? And even more interesting, even if we're off a little bit, it's still going to work. Because we're only going to get a very slow sinusoid. And now I have to go back to PowerPoint to draw. I'm only really going to tell you that if omega minus omega wiggle is small compared to our integration interval, let's say that ends up being 10 hertz, and then we integrate only over 1 millisecond. 10 hertz over 1 millisecond is basically ignorable. Doesn't matter. 10 kilohertz over 1 millisecond is a big deal. Then we have several periods of that sinusoid, and then it doesn't work anymore. So if we go back to Mathlab, so let us say this here, and this is a little bit of an illustration of what I just talked about. So the phase between the incoming signal and the LO, the local oscillator, the other sinusoid that we multiply with is 0. For the first one, the frequency offset between them are also going to be 0. Then this is what we're going to end up with. So in one of them, I and Q, we have no phase, meaning that In this case, everything ends up in Q. Nothing ends up in I. And the resulting complex acquisition, we get 23.9 dB, which is what we expect. And all right. Yes. So this first figure right here is the carrier frequencies, right? Up in the upper left and the upper right. The second figure has a PRN code multiplied with the sinusoid. So here, the I channel was 0, so whatever is here is also going to be 0. And then for this, where this is 1 all the time, we end up with the PRN code. All right? And the third one is the acquisition of the each channels. Does it make sense? So let's make it a little bit more interesting. Let's say we have start 90 degrees offset here. Go through the plots, basically what we expected, right? We move all the, we now have 1 in the I channel, 0 degrees in the Q, still works. Where the PRN code ends up is just the other window. Nothing really changes otherwise, all right? Let's do it one more time. That we put in 270 degrees, still 0. Look at this one. Now -1 here. Of course, you can't tell the difference for the PRN code, but it's actually inverted compared to the last example. And if we look at the last one, we get the peak going down instead. But the bottom plot shows just the absolute values of those, so it doesn't matter. All right? Let's put the phase back at 0, but let's put in a bit of a frequency offset. And I've got no idea what to start with here. I'm going to start with 1,000. All right. And it was 1 millisecond. That's all good. So let's say this is what it looks like. Is this going to work? Now we end up with a sinusoid in both cases. They're 90-degree offset from each other. And if you look at the bottom plot, it doesn't seem to work, right? So what happens? Why doesn't this work? Any ideas? Suggestions?
You're not getting the full PRN code.
Yeah, but you're not only not getting the full, you're not getting any. What happens if you integrate sinusoid over a full period? 0, right? Which is exactly what we do. If you look in the top, in this one right here, we multiply this with a code, but let's just look at this. If we integrate this, we get 0. Integrate the other one, we also get 0. Doesn't work, right? And this was of 1,000 hertz, which corresponds to a full period in a 1 millisecond window. So let's try this again. Put the phase in. Let's put it down to 500 hertz difference instead. Now this time it seemed to work. Which makes sense, right? So if we look at the left plot, if we integrate that, half a sinusoid, then we actually get some energy, right? If we look at the right one, we get 0 in there. But we still pick up enough energy in the left one. There's just a PRN code multiplied like that. And just like I hinted at, all the energy we get in the first one. Does it make sense? If you've never done any signal processing before, this is going to be all new concepts, kind of like, but And of course we can do the same thing. Let's put in a random phase between them. Let's put in this 500 Hertz, or let's say 250 Hertz in this case. And look what happens. Here we have a little bit less of an error. Apparently we ended up, my phase offset was a little bit too close to 0 and 1, but can't really be blamed. I had no idea where that was going to end up. And if we look at PRN code in the INQ channel, this is what happens, right? And this makes sense. So if we integrate this, we're going to end up with a negative number, which is why we have a negative peak here. We integrate this, we end up with a positive number, we get a positive peak. We take the square of both, we sum them together, and then we just get the square root to normalize it again. And compared to the original case, where everything was perfect and we have 24 dB suppression, we'll lose a couple of dBs here. 2.5, basically. But that only has to do with us being off in frequency. So it's a little bit, again, a little bit of a trade-off. We could try an infinite number of carrier frequencies, but we're never going to finish. But we're not going to take much of a loss at all when it comes to this issue. But, so, the more sensitive you want to be, the more narrower spacing you want between your carrier frequencies that you test for the acquisition. Let's keep going. I got plenty of demos today. This one really does. Come on. This is the one. Let's skip that for now. Because see, this one talked about serial search algorithm. Let's jump back. 4. Does anybody remember this number? 192, right? It's a little bit of a gamble here. So this is basically the Mathlab implementation of the serial search, which works just the way as the FPGA did. So we have the incoming samples, we generate the codes, different offsets, try all possible combinations, multiply big vectors, we end up with a result, right? And it's awfully slow. I'm not even going to let it finish. Part because it's just boring to wait, and part because I've got no idea if I actually put in the right numbers, if I'm actually going to find anything. But as an illustration, it still worked. And this is what the results would have been. All right. Last week, when we looked at the correlation, we only saw it as a two-dimensional plot, right? Only as a function of code phase. Actually, I was on the right data set anyway. This was PRN12. I probably would have found it. I'm pretty awesome. So here we have the code phase. Here it's not expressed as samples, but rather the ships. Right, which is why it goes from 0 to 1023 rather than 0 over to whatever 1 millisecond of data sample at 38.192 megahertz would be. And here, if we kind of squint a little bit, we can see that it kind of looks like a triangle in this space, right? If we look from this side. From this, it seems wider in some cases. And what we actually have here is something called the sync function. You can't really validate that this is what it is just from this picture, but trust me, it's a sync function. And it's all buried in noise. Well, it's not buried in noise. It was noise before. We found the correct code phase and carrier frequency, and we brought the signal up above the noise floor, right? You have a clear peak. If you look at this, I would say, without a doubt, we got a signal here. And this is basically what acquisition does. It searches this space of code phase and carrier frequency, and we try to find this signal. Try to look for PRN12. At the time of that data collection, it was unallocated, so there were no satellite that had PRN12. So we are 100% sure that at that time it was not transmitting, and we couldn't find it in the data set, right? Here it just looks like noise. And this was a couple of years ago. PRN12 is now allocated again. And if we look in the, we take that peak and wherever that was, and then we just look at the two spaces, functional code phase for the correct one, and then carrier frequency for the correct one. So we're basically looking here. Does that make sense? And we have this, what is a triangle in the code phase, difficult to see, and this kind of, yeah, can show this is a sync function again, but that's how it works. The sync function is just sinus of x divided by x. If you plot that, you see that it's interesting. It shows up everywhere when you have modulation of signals in stuff. So how do we decide? So I looked at this and I said, hey, there's a signal there. Do I have any kind of basis for that? I mean, it looks like a short peak, but we need some kind of metric, right? And this is what the book code uses. So we'll look at the strongest peak, whatever that value is, and we divide that with the second highest peak. And the reason we do this is a little bit complicated. So if you record data, and you know for a fact that this is only a GPS signal and Gaussian noise, then you can really just look at whatever the variance is of the noise and use that your noise floor, go through acquisition, you get a peak, and you can predict if I have a signal that is at, if I have a positive SNR 20, then this is what I expect, basically. You can figure out how strong the signal is just from acquisition. The problem is that that assumption only really works if you know that you have Gaussian noise. And basically, you typically don't. You're going to have other GPS signals in there that are non-Gaussian. You're going to have possibly interference, even though nobody's allowed to transmit in that band, but still stuff leaking in. Sometimes stuff breaks and starts transmitting in the L1 band. It's a bit of a problem. You also have kind of analog effects coming in that messes up the Gaussian distribution of that noise, which is why we like this peak to second peak approach. Does it make sense? So just a ratio between the two. And here we say that we have a signal. Here the ratio is close to 1. There's no signal there. And this is where the cutoff is, if you look in the settings.m in the book code. Questions? Yep.
So your next highest peak, are you getting that from the two-dimensional search space? Or
yes. So this second one here, this one, we just look at whatever the highest peak is. And let's say it was this one. Then we go through and we just look at this one. I think that's how the code does it. And then,
the second highest peak you're just getting from the one-dimensional cut?
yes, exactly. Just to make it simpler. The problem is that you have, it's pretty wide in this space. So in order to find the second peak, you have to first get your data, and then you have to put the peak and a couple of samples around it to 0, and then you can find the second highest one. If you want to do that for a full space, then you have to take out the entire sync function, and it's just messy and doesn't degrade that much for this. Does that make sense? All right.
Can I use the restroom?
Sure. I'm not going to wait for you though. So, here we got some key questions related to acquisition. I've kind of hinted at half a ship. It's kind of like the spacing we want, right? I did show you why we needed a kilohertz stuff, right? Or does this contradict what I said? You saw that it broke down completely when we were 1 kilohertz off, right? But since we're going to try, if we take 1 kilohertz steps, that means that the next one is going to be perfect. Right? So if we take 1 kilohertz steps, we're never going to be more than 500 hertz off. Make sense? So we have a couple of... So this is our steps. 1 kilohertz. And regardless of where the signal actually is, we're always going to be within 500 hertz. Does that make sense? And the same kind of logic goes for the code phase step. If we're okay with half a ship, then we're actually never going to be more than quarter ship off. This one, do we need to test everything? Hint at that too. Validation. Then we get into the interesting stuff, the speeding up, and how to make it more sensitive. And the last piece is what the next assignment is going to be about. I don't know what it's doing right now. It doesn't. Oh. All right. So, the code phase steps. Half a ship. We'll look back. The triangle. This is just a sample. I don't know exactly. This here was 2 ships, right? So this here is 1 ship. And here we have like 1, 2, 3, 4, 5. So we tried a little bit closer here. But we're guaranteed to get 75% of the signal energy if we take half the code phase step. Does that make sense? So let's assume the best case, basically. We're perfect. Let me do this as pluses. Perfect, we're going to end up here. We're going to end up here, 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 right? This is a perfect case. If we try half a code phase step. And if we look at the worst case, it's going to be right between here. And keep going on like this. Does that make sense? And if we look at this, I can't draw worth down, but still, 0.75, 75% of the max. Does that make sense? Which seems like a reasonable trade-off, right? I mean, if we can't bring it down too much. So if we only get, and that happens pretty quickly, if we start going for more than half a code phase step, then we get like down to like 20% of the signal energy, then it doesn't feel right anymore. In order to get much more than 75%, we have to increase it. It's like a reasonable trade-off. So that kind of makes sense, right? This one we looked at before. Looked at the integration, different sinusoid, 500 hertz. We are guaranteed to get some signal energy. And it's basically, one way of putting it is you don't want 0 crossings. Too much. And I think you understand this, right? Everybody's happy, content. And this one, do we have to try all code phases and frequency bins? And this one comes down to the answer to that one. Let me go back here. The answer to that one is basically no. Not always, but some of the time. So let's assume we have a cold start. We don't know anything. Then we are going to have to try everything. Try all the code phases. We have no idea where the signal is at. On that kind of accuracy, frequency, we got no idea. But let's say we know roughly where we're at. And we know roughly what time it is. And we managed to find one PRN signal. And we tracked that for a little while so we know what time it is. Pretty close. Then we can actually use the almanac that we assume that we have already. Predict where the other satellites are going to be, and from that predict whatever that Doppler is going to be. So the more information we have, the more we can reduce the problem.
Can you ever actually go to a pure predict standpoint?
Yes, you can.
Type stuff?
Yes. For some special applications, this is what you end up doing. Radio occultation being the one that comes to my mind. So we have the Earth here, GPS satellites orbiting, then we have another satellite orbiting in a LEO orbit, or I shouldn't say LEO, I want to repeat words. And what happens here is that when the GPS satellite sets, or the distance between the two satellites, the signal is bounded by the atmosphere, basically. And if you look at that signal, you can figure out a lot of stuff about the atmosphere that you can't get any other way. GPS is very popular from that radio occultation standpoint. The occultation is bending of the signal. And then you have exactly that thing going on. You track it for a while, but then you basically predict where it's going to end up. And you track it that way. But it's not in a sense, depending on what kind of information you're looking for. If I just go directly to say this is where it's at, well, I have to track it to get the precise information. Otherwise, I don't add any information to my receiver, right? If I just say, well, this signal is going to be here, so I'm not going to bother tracking it, then I kind of don't get that information. Does that make sense? All right. What about validation? We have a signal and noise here, right? Which is, of course, ends up being one of those annoying statistical problems. Noise, it's kind of noise. Sometimes we're going to end up finding a peak where there really isn't a peak. Not for the clear-cut cases, but for the weaker ones, it's a little bit unknown. So how do we know that the signal really is there? Do you have any ideas?
The high is the peak and the second high is the peak.
Yes, but that's just the first kind of step. What can we do after that to validate that we actually have a signal?
Run the search on another data segment.
Yes. So we know the code is repeating, right? So we found it with a certain code phase and frequency. In this data set, we can look 1 millisecond further ahead. Do we have the same code phase? We should find a peak there too. Or we could start tracking and just throw it out if it doesn't work. So there is what we typically talk about. Probability of false acquisition. So we can change this value of the threshold where we say that we have detected a signal. We can set that to whatever we want. But we always have a probability of false acquisition, meaning that we detect a signal that isn't really there. All right? There's one problem. We have a signal, we don't detect it. No, sorry, we detect noise rather than a signal. That's the first problem. The second one, probability of misdetection, is the inverse. We have a signal, but we didn't find it. So for a certain signal strength and a certain ratio, we can figure out what those values are. And we want the probability of false acquisition to be low, and we also want the probability of misdetection to be low. But again, it's a bit of a trade-off. We can't always, we cannot not miss a signal. It's a bit too many negatives here. And at the same time, as we're never wrong when we find it. In that case, we need stronger signals, or we need a more sensitive algorithm. Does that make sense? This is what we decided, right? We have a periodic repeat of the code, should show up in the next millisecond. We can also look at the post-correlation frequency domain data. And now it gets a little bit weird, but let's start with this one. This is what happens if you do acquisition continuously, basically. So we have one peak every millisecond. And here, of course, we have a very strong signal, so I'm still, even from the first one, I can say we definitely have a signal here. I don't know what the ratio peak to second peak would be here, but strong, 4, something like that. But then we also have this periodic repeat, so now it's like clear cut. We know we have a signal here. So if we look at the spectrum of this is a 38 megahertz data set. And let's say we only do one of those things. I showed you that we do mixing with the sinusoid and cosine, and then we also multiply with the code, and then we integrate, right? Let's say that we only multiply with the sine and cosine. That's all we do. And then we look at the spectrum. No, the other way around. Let's say we only multiply with the code, and then we look at the spectrum. What do you expect would happen? Any suggestions?
Correlation gain on the signal, so it should be popping up above the noise floor.
Exactly. So we basically expect a peak in here, right? It's going to be off a little bit depending on that. And if we go back and look at what does the spectrum look like for different signals. Sine wave, an impulse in the frequency domain. If we talk random bits, then we get a sync function. It's only drawn as a, I don't know, I should fix this plot basically. It should look like a sync here if we look at this one. It's going to pop up a little bit right here. So we take the signal, the sinusoid, we spread it over a wider band, we transmit it, we receive it, and then we despread it. So we multiply it with this code. Then we basically should get a sinusoid back, right? Which is why I would say that we should get a peak here. That is, fortunately, exactly what happens. So this here is just a shorter piece of the spectrum. I think it's a different data set this time, doesn't matter. And then when we find the correct code phase, we get this spike, right? So what do we do here? And this is if we do several of them. You see here the shifts, 12,049, 53, 57, just depends on whatever your sampling frequency is, and then you take a step, about half a ship. And here we can see that, whoa, this here is roughly the code phase that we're interested in, between 12,061 and 12,065, right? So why would we do this?
Faster.
It should be, but it isn't. But that doesn't matter. Basically, that's what it comes down to. So we have our 3-dimensional search space, or 2 if we just look at one PRN number, code phase and frequency, right? And here we basically simplified it so that we don't have to look for the frequencies. We do that in the frequency domain, and we only have to try one of the parameters, right? So from a algorithmic standpoint, this would be a better way. Now this turns out not to be that very practical for other reasons, but still it hints us, right, that we can do something cool here. And this is the, again, same as the FPGA block diagram. This is called a serial search, the slow one that I showed you, right? Took a long time to find the signals. And if you compare that to the book code that you ran for assignment 1, was it faster or slower? How long time did acquisition take?
Do they use the parallel search?
Yes, they did. So the acquisition with the book code was much faster than the example I showed you, right? I mean, we kept going on forever. Many seconds, basically. So there is a better way to do it. I already hinted that the parallel frequency approach is not that much faster, right? It should be, but there's too much there. Showed you this one. So serial search, we need to try all of these parameters individually. So we have this cube we have to search. Not much else you could do, at least historically in FPGAs. Nowadays it's all messy and different and they won't tell me what they're doing. I just have to infer it. But let's say we have the data instead, like we do in Mathlab. What else could we do? This is one thing. The parallel frequency approach. So we try all the different code phases, but for each time we compute the FFT and then we look at the peak. The thing is, computing the FFT takes too long for it to be practical. But it's still interesting as a kind of a, seems to be something here, right? If I just gave you no other instruction, there is a PRN signal in here, you had some idea about it, you would implement a serial search. That is kind of like the straightforward approach. It's not trivial to come up with something better on your own. Fortunately, there are many scientists and smart people in the world that think about stuff. So this is what the parallel frequency approach would look like. We have samples, multiply with the PRN codes, we do the FFT, we have some decision logic. And then we try other PRN codes, right? The problem is this, we have to do the FFT for each code phase. That takes longer than what we wanted to do. But it does work, right? Signal pops up above the noise floor. I don't know what it says, unfortunately, here. But the thing is, if we have, I don't know what I would replace it with, actually. If I put it a little bit into context, go back. Let's say we have the almanac, we have some idea where the satellites are at. Then we actually can predict what the Doppler is going to be, so we don't have to search the carrier frequency that wide, right? This makes the problem better. The problem is the code phase. The uniform random variable, the larger space. If we only talk 1 millisecond, we want to have half a code phase. Then we have a 2046 tests that we need to do. In frequency, it's much smaller. It's like 10. The code phase is the biggest one. So, if I put it this way, maybe you've heard this before. Multiplication in the time domain equals
Convolution.
Exactly, right? So convolution. But we don't want to do convolution, right? We want to do correlation. They're kind of related. I assume you have seen the convolution integrals in some class, right? Anybody have never seen convolution? Everybody's seen it. I assume not too many like it too much. It's a little bit messy, but it's a fundamental, basically. But we have this really cool thing, that multiplication in the time domain equals convolution in the frequency domain. I'm not going to try and put down a convolution integral right now. But there is a relation between the convolution and the correlation, which hints us this one. We can do the entire code phase search in parallel, and now it's get interesting. So rather than try all these 2046 different values, we can do that in one big test. And if we know where we are, we can figure out the carrier frequencies, so we only really need to test one frequency bin if we know stuff. Typically in this class we never know stuff. It's too messy to implement all that stuff to figure out where the satellites are at, but I want you to know that this is how you do it in a commercial kind of receiver. And how does that work? There is a relation. Let's say we do it the other way. We have the carrier mixing. For some reason somebody put in a filter here, I don't know why. You can do it if you want. Compute the Fourier transform. I should bring this up right now. So, we have the Fourier transform, right? We have the continuous Fourier transform. Just the integral kind of thing that you look at. I don't remember exactly how it looks like, doesn't matter. We have the DFT, the discrete Fourier transform, right? Which is a different one. But it's just the same, it's the sum, a couple of different parameters back and forth. And I'm sure you also heard the term the FFT. And what is that?
Fast Fourier transform, it's a fast
Yes.
algorithm to compute the DFT.
Exactly. So the DFT you could compute over whatever parameters you want. The FFT is a fast way to do the DFT, but typically you can't input whatever parameters you want. It gives you, depending on whatever data you feed it. And if you use, there's also something called the FFTW, which is supposedly the fastest Fourier transform in the West. That's what it's supposed to mean. It comes out of some university, I forgot which one. And they do whatever tricks they can to make it as fast as possible. And that's the one that Mathlab uses. This is basically as fast as you can do it. So Mathlab just takes the FFTW and then wrap it around so you don't see it. But it's inside there. You can play with it if you really want to. By getting out of it, basically, a little bit. So we have the signal, we do a Fourier transform. We have the same for the code. We do a Fourier transform of the code. And this here is the extra step that comes into play. I said that convolution and correlation is related to each other. And the really only difference is that multiplication in the time domain equals the conjugate. There's no good way to put it. But basically, if you add the conjugate of the Fourier transform in here, you end up doing correlation instead of convolution, which is pretty awesome, right? So we take this, instead of searching 2046 chips, just do an FFT. Multiply them together. So rather than trying 2046 different steps, and each step requires a multiplication of 2046 values, right? So instead we do the FFT, then we do one multiplication, that's all we need to do. So rather than 2046 squared, we have 2046. That's pretty awesome. The inverse Fourier transform to bring it back to the time domain. Then we have the same stuff, magnitude, decision logic. This is pretty awesome, and this is how the book does it so fast for the acquisition compared to the serial test that I showed you. That I'm going to do now again. Do I have several Mathlabs open? No? What's going on here? There we go. 21, right? 9.55 E6. 38.192 E6. This time I'm actually going to run it to see if I actually was correct or not. And this is a slow one. The book code is much faster, right? But this is a direct implementation of the way historically they'd used to do it in the FPGAs. Nowadays, if you have your runner's watch or whatever in your cell phone, oh, we're not going to wait for this. In your cell phone, they actually implement an FFT version in the FPGA. That's because it's so much faster. And we're not going to finish this. So with frequency step 3 out of 41. And it's this slow, basically. So I'm not going to wait. So let's do the same thing with the FFT approach. 21, right? I think I put in the same numbers. There we go. Was a little bit faster, right? This is a fun demonstration to do. You could basically barely see it happen. And this was a pretty the data set with a very high sampling frequency too. It's about 40 megahertz. But this clearly shows up here. PRN21 is here. No, I don't know what's going on. I should have closed all the other figures first. Everything is messed up. Let's do it again. It's so quick that it doesn't matter. Now it makes sense. So this is what we have. And if we look in the two, here's a function of the frequency search. And this one here is a code phase, raw, and then when we zoom in. Pretty awesome, right? Frequency domain. Awesome. So we have a way to do it with all of the code phases at once. It was super fast compared to the other one. And this is a block diagram what the book code does. So pre-allocate arrays. Why do we do that?
Faster.
Why is it faster?
You already have the memory allocated, so you don't have
Exactly.
to allocate
So if you have a Mathlab matrix or something, and then you just keep on adding random numbers into it, every time you add something that is outside of the size of it, it's going to have to allocate a new matrix. Copy all the information over and then add your new value. And if you keep doing this in a loop, then it's messy. It's going to be an extreme overhead. It could be ridiculous if you do it wrong. So make sure you pre-allocate whatever you can pre-allocate. When we do that, we take the PRN code, convert it to the frequency domain. It says DFT here, but it actually is implemented as an FFT. Generate the sinus and cosine signals, mix it to baseband, take the data, mix it to baseband, and transform it to the frequency domain. We'll multiply this one with this one, do the IFFT, and then we just keep going till we've tested all of them. Then we'll look at the metrics, find out if there is a signal present, all right? And this is basically the first half of the acquisition function. For the second half, in order to start tracking a little bit better, then we actually try to find a better estimate of the code frequency. No, not the code, the carrier frequency. So we have figured out rough estimates of the code phase and the carrier frequency. But in the next step, we want to have a finer estimate of the carrier frequency. And then we actually do this parallel carrier search. So we already have multiplied down, so we expect the sinusoid and noise, compute the DFT, and we find a better estimate of the frequency that way. That's what happens in the second half of the acquisition function. For the assignment 2 that's coming up, I want you to basically remove the second half because it's not going to work that well when you have weak signals. For the acquisition challenge, you're going to try to find as many signals in a particular data set as possible, but the second half is just going to break down, so don't worry about it. Does that make sense?
Except for the second one, we're just finding the signals. We're not
Just find the signals. You don't have to worry about it actually moving over to tracking, because tracking is not sensitive enough to pick up whatever stuff, but I can't have you do everything at once. I'm going to start with acquisition. And this here is an example of what it could look like. So I talked about the almanac. We get the orbital parameters for all the satellites. We know roughly where we're at this time. University of Colorado, 40 degrees north, 105 degrees west roughly, about a mile over the mean sea level. And this is what the prediction tells us. And this is a sky plot. Those are going to show up later on too. And they're actually in the last, when you do the navigation solution, right? So the middle here is straight up. This point right here is directly north. That way, right? Roughly. This way is directly east. And then so for a random point right here, it's going to be east-northeast. And then whatever here, this is straight up, 90-degree elevation. The elevation is starting from the horizon and then up. So this one is going to be pretty high up. So 21, for example, is basically directly east. About 65, 70 degrees elevation. But of course, if we can compute that, then we can also compute what we expect the Doppler to be just from the satellite moving relative to us. All right? You also have user Doppler, but it's typically much, much smaller. So if you're car on a highway, but that doesn't move very fast compared to the GPS satellites, right? What does mess it up a little bit is if you accelerate. It actually does come into play, but now I'm getting too far ahead again. So if we take this one, say we know where it's at, and we go through acquisition, these are the satellites we expect to find, right? And with the simple 1 millisecond acquisition, these are the satellites that we found. We only found 8 of the 12. So there should be other signals present, but we couldn't pick them up. And there could be a couple of different reasons. One could be that there's something blocking the signal. So just because it's visible in free space or open sky conditions doesn't necessarily mean that it's visible where you're at, right? You could have a big-ass building blocking something, and it doesn't work. You could have canopy, basically, reducing the signal power. So it's difficult to pick up. All sorts of stuff comes into play. Not to mention reflections. And next, we're going to do this bigger, faster, stronger. Let's try to find some weak signals. I will post it later today, assignment number 2, together with the groups. If you got the book, it's chapter 5 and 6. So read on. And also, I never posted my lecture from last week, lecture 3. You're going to have to give me some crap for that, so I actually post it, because I'm going to forget. But I'll try to both this one and that one up today, too. Any other questions? And like I said, you have 2 weeks for assignment 2. Just because it's a little bit more time-consuming. Also a lot of fun. You compete against each other, in a sense. But you're not graded that way, but let's see who does the best. Any questions? Or am I just miraculously clear on everything? All right. I'll see you Wednesday.